this example, I have two equations. Neither one of them is linear. Okay, in the first one, I have a circle of radius 4 centered at the origin. In the second one, I have a parabola because one variable is squared, the other is not. What I might do is very quickly, very briefly sketch a graph. I wouldn't give a lot of detail, but at least it would give me enough information to know what to expect for solutions. So this top equation is, of course, a radius 4 circle centered at the origin. So 4, -4, 4, and -4. And then the second equation is a parabola. Now, to get the graph of the parabola down, I could, this one has y as the linear term. So if I solve for y, I get a fairly decent idea of the graph. So if maybe I add the two y to both sides, and then subtract the 8. Jumping ahead of myself. Subtract the 8 and divide out the 2. And so I get 1/2 x squared minus 4 equals y. Well, what I know about this parabola is it's shifted down 4 units, and it opens wide, a little bit wider than x squared because of the 1/2 coefficient. So being shifted down 4 units, it's going to have a vertex right on the right at the point -4 there, 0, -4. And then it opens up. Now, to figure out how wide it opens up, I don't know, it could open up kind of on the inside of the circle, it could open up on the outside of the circle, it could kind of hit the edge of the circle as it opens. I'm not exactly sure. So there's some options here to get a little bit more detail. If I knew where the x-intercepts were, I would know whether it opens up inside or outside of that circle. It might be a good clue. So just to briefly get the x-intercepts on this thing, again, I'm not really solving the system. I'm just trying to figure out whether my solution will be reasonable based upon the graph, okay? The x-intercepts on this thing, if I plug a 0 in for y, I get 1/2 x squared minus 4 equals 0. Add the 4, multiply by 2, I get x squared equals 8. So x is plus or minus the square root of 8, which is 2√2. And if you evaluate 2√2, you get approximately 2.8, roughly, right around 2.8. Write that a little bit nicer. So it's right around 2.8. So definitely going to be on the inside of the circle. Okay, so the 2.8 and the minus 2.8 are going to be the two x-intercepts there. So definitely on the inside, which tells me there are I'm assuming there are three points of intersection. I can't even say that sentence right. One is at the vertex here at 0, -4. But I'm still going to solve it and make sure that that's there, and I'm not just making a mistake in my graph. And the other 2 points appear to be up here in the first and second quadrants, respectively, and they're up symmetrical. It appears that there's some symmetry here. They're going to be at the same y value, if I could plot that, and then equidistant on either side of the the y-axis. So yeah, we'll see. So hopefully our solution, when we get that far, will be consistent with that idea. Okay, so I always like to look at the graph just to get an idea of what I'm looking for, and then I go through and solve. So now I'm going to go through and solve. In solving this, I see a couple of squared terms: an x squared, a y squared, another x squared, and a y. Usually, if there's a repeated term, like in each of these, there's an x squared. You could use substitution and solve for one of them and substitute it back into the other. Okay, so this is just a general rule. If there's a repeated term, a nice strategy is to solve for one of them and then substitute it into the other one. So here I might solve for x squared, and actually let's go with the second equation here. So let's number these 1 and 2. I'm going to take equation 2 and work with that. If I solve for x squared, I'm going to get 8 plus 2y, add the 2y to both sides. And then I'm going to substitute 8 plus 2y in for the x squared in the first equation. So this becomes 8 plus 2y plus y squared equals 16. This now becomes a quadratic equation with y as my variable. If I rearrange these terms, I'm going to subtract the 16 from both sides and then rearrange them in descending power. I get y squared plus 2y minus 8 equals 0, right? 8 minus 16 is negative 8. This is factorable. I could do x minus 2 times x plus 4, right? Negative 2, positive 4. Their product is negative 8 and their sum is positive 2. Then I can set each factor equal to 0. X will be 2 from this one, and x will be negative 4 from this one, okay? So that gives me two apparent solutions, one with x equal 2 and one with x equal, oh, I just went with x. Oops, guess what I just did? These were y's, not x's. Those should be y's, not x's. That's very, very important. Must keep the variable consistent. Okay, you can't change the variable in the middle of the problem. That wouldn't make any sense. Don't get in that habit. It's so easy to just write x's in those parentheses. Yes, we don't want to do that. So those are y's, sorry. So y as a 2 value and y is a negative 4. So apparently I have two answers, but let's just work this through and see what happens. I want to take each of those and plug them back into one of the two equations. It shouldn't really matter because the intersections, should give you the same points on each equation. I like the circle a little bit better than dealing with all these variables and negatives. That's just me. You can put them into either of these. So I'm going to go with a circle. So let's go with a 2, for instance. If I plug a y value of 2 in, I get x squared plus 2 squared equals 16. The 2 squared is 4. If I subtract 4 from both sides, I get 12. And square root property, x equals plus or minus root 12, which is plus or minus 2 root 3. Okay? Because there are two solutions here, that really gives me 2 points. So with a single y value of 2, I end up with both the positive and negative 2 root 3 as x values, which kind of makes sense. On our graph, if I had a fixed y value of 2, I should have symmetrical points, positive 2 root 3 and negative 2 root 3 as the x values. So that kind of makes sense. My graph is definitely not to scale properly here because the height of those points should be at 2, not at almost 4. I have it. But that's not the point of the graph. The point isn't for accuracy, the point is for reasonableness. So I'm going to go with what we have here. So that tells me 2 points. One of them is at 2 root 3 comma 2, right? X value, y value, and negative 2 root 3 comma 2. So I'm taking the positive and negative x values, matching them with the corresponding y value, okay? Now I go to the negative 4. And if I plug in the negative 4, so x squared plus negative 4 squared equals 16. Negative 4 squared is 16. Subtract the 16 from both sides. I get a 0. And of course, if x squared equals 0, then x equals 0. Plus or minus 0, but it won't matter. Okay? And so here I have another point. It is 0 comma negative 4. These are the 3 points that seem reasonable based upon the graph. However, it's always good to check these as well. If I were to check them, 2 root 3 comma 2. Now, what I didn't do is, I solved them on the first equation, so what I should do is check them on the second, okay? So the check is going to be done on equation 2. 2 root 3 squared. Remember, 2 root 3 comes from root 12. And if you square it, you just get 12. So that's 12 minus 2 times 2, right, the y value is 2, equals 8, and of course 12 minus 4 does equal 8, so that one checks out. If I do the negative 2 root 3, when I square it, I'm going to get the same thing, 12. And then the 2 here is going to be a minus 2 times 2, which is 4. So that one's going to work out as well. And then, of course, down here, 0, negative 4, plug a 0 in. Negative 4 times negative 2 is 8. That matches, so they all work out. You know, I'm not going to write out all the work there just to save a little bit of time on the video. But generally, you would want to show all that work as well. So it appears that my solution set, and you always want to write your solution set out, is going to be 2 root 3, comma 2, negative 2 root 3, comma 2, and 0, comma negative 4. There's my final solution set, all 3 points of the intersections. Now, there is another strategy to this. I used a substitution method. You could use elimination on this, okay? An elimination with this, let's get rid of all that. Elimination instead might say, if I'm working with these two equations and I know I have that common x squared term, it might be easier to eliminate them by adding the equations together. And one way you can do that is to multiply one of the equations by negative 1, sorry. So if I were to take this second equation, multiply it by negative 1, I would get negative x squared plus 2y equals negative 8. And then if I were to take this first equation and not change it, I would get x squared plus y squared equals 16. Sometimes I say I multiply that by 1 if I'm not changing it. And then I add up, right? Elimination is where you add up the equations once the variables have opposite coefficients. And so here the x squares go away. You end up with, well, these two are unlike terms, so I got to write them both down. Y squared plus 2y equals negative 8 and 16 is 8. And of course, if I get a 0 on one side, I'm going to have the exact same equation we came up with doing the substitution method, right? So we'd have what, x minus 2 and x plus 4, and that led us to our 2. See, I did it again with the x's, didn't I? I always want to factor it with x's. I don't know. I have a habit of that, and it's bad. Go with y's here. Variable is y, you got to go with y's, and then that tells you y equals 2, y equals negative 4, and then you could continue the same way we did before because those are the same two y values we found earlier. Okay, so in reality here, both the substitution and the elimination methods give us the same result, and really almost look identical. From this point on, they are exactly identical.